Hi everyone, these are the notes for section 1.5. We began with definitions, explaining to you what a relation, domain, and range are. A relation is any set of ordered pairs. By ordered pairs, we mean x, comma, y, where you have an x and y coordinate. Domain is all of the first entries, or in this case, all of the x coordinates. The range is all of the second entries or all of the y coordinates. Now let's suppose we had S, this relationship, with 1, 2, 3 ordered pairs. We have 2, 3, -5, 6, and 7, -1. Identify the domain. And remember, the domain is all the x coordinates. So we would list all of the x coordinates, 2, -5, and 7. So 2, -5, 7. The range would be all of the second entries or the y coordinates. So the 3, the 6, and the -1. We would list them. 3, 6, -1. Is S a finite or infinite relation? Now these terms, finite and infinite should stand out to you. We know infinite as being infinitely many. So it would mean that the term, or the S in this case, would run on forever and ever. There would be no stopping point. Finite means that you can count them and there is a stopping point. So we can clearly count the three portions of the domain, the 3 terms in the domain and the 3 terms in the range. Therefore, this would be considered a finite relationship. In the next problem, we're asked to plot this point, -4, 3, and we want to know in which quadrant does this point lie. So here's our coordinate plane. Let's imagine that each of these spaces, we have one space between them. So 1, 2, each line will represent one space. 3, 4, 5, 6 on the x coordinate. And then when we move to the left, we'll have -1, -2. Now, how will we plot this ordered pair? Remember, the first point is your x coordinate, the second is your y coordinate. So -4 on the x-axis. We start at 0 and move over 1, 2, 3, -4 spaces. And then on the y-axis, we're going to move up to 3. So we're moving left, 1, 2, 3, 4, and up on the y-axis, 1, 2, 3. Here, we plot our point. That's the ordered pair of -4, 3. Now, after we plot the point, the second part of the question says, in which quadrant does this lie? Remember, you have 4 quadrants in the coordinate plane. In the upper right-hand corner, that's quadrant 1, and we use Roman numerals to represent the quadrants. Moving left, move counterclockwise. The second quadrant will be in the upper left-hand corner, and then in the lower left-hand corner, we have quadrant 3. In the lower right-hand corner, we have quadrant 4. So where is our point? It's right here in quadrant 2. I'll just put Q2. Now plot the origin. In which quadrant does this point lie? When we plot the origin, that is at 0 and 0 on the x and y axes. So I'm going to draw another coordinate plane here. Our y axis and our x axis. The origin will be right here in the middle. Now here is our quadrants, 1, 2, 3, and 4. Origin isn't in either of those 4 quadrants. So it's not in a quadrant. To answer this question, in which quadrant does this point lie? None. It lies at the origin. It's not in a quadrant. Okay, so some of the points that you plot will be in one of the 4 quadrants. in the quadrants, like the first example, but other times you may plot a point and it'll be directly on an axis. Like if I were to plot this point here, it'll be directly on the y-axis, or this point here would be directly on the x-axis. Now let's look at the next example. Suppose you have y equals 5x minus 2, and you're asked to use this rule. By rule, we're referring to the y equals 5x minus 2 to complete each ordered pair. Now we see our ordered pairs, we have 3 of them here, and we're given x coordinates for each, well, we're given x coordinate for the first 2 points, and then we're given the y coordinate for the last point. What we want to do is we're going to take each of these ordered pairs and we'll substitute the variable, the value that's given to us, to solve for the missing variable. So in the first example, we're solving to find y. In the second one, we're solving to find y. And in the third one, we're solving to find x. So let's start with the first ordered pair. If we have x equals -2, we want to use our rule or our equation that was given to us at the beginning, y equals 5x minus 2. And we're going to substitute -2 for x. We'll have 5 times -2 minus 2. Now we'll simplify this. 5 times -2 gives us -10 minus 2, which will give us -12. So our y coordinate for this first set would be -12. Now for the second set, we're going to substitute x equals 8 into our given rule or an equation, which was y equals 5x minus 2, and we're substituting 8 for x. That'll give us 5 times 8 minus 2. 5 times 8 is 40 minus 2. Our y coordinate is equal to 38. So here our y coordinate is 38. Next, we're going to substitute y equals 7 into our rule or given equation, which is y equals 5x minus 2. And now we're substituting 7 where y is. So we'll get 7 equals 5x minus 2. We want to solve this equation for x. The first thing we want to do is add 2 to both sides of the equation. We'll get 5x, because the 2's will cancel on the right side, bring down our equal sign, and 7 plus 2 gives us 9. Divide both sides of the equation by 5. The 5's will cancel. So x equals 9/5. So right here, our x coordinate is 9/5. How many ordered pairs could you create using this rule? For example, or in other words, how many solutions can you find to this equation, y equals 5x minus 2? Explain. Now, how many solutions can we find to this equation? That means how many different x and y coordinates could we plug into this equation? There are several, because all we need to do is come up, just like we did for this last example, we can come up with a bunch of ordered pairs. We can substitute any numbers for x or any number for y, and then determine what the y coordinate would be. That list can go on and on forever. We can plug in a whole bunch of different numbers. There's infinitely many options. We can plug in any number for x to solve for y, or any number for y to solve for x. So there's infinitely many solutions that we could choose. Would this set of all solutions represent a finite or an infinite relation an infinite relation. Remember, there are infinitely many. List 4 ordered pairs that belong to the relation determined by the equation below. So we're given some equations and we just want to find 4 ordered pairs. So we can create a table for ourselves using the variables as given. So in the first equation, we have variables t and a. So let's create a table just like we would if we were creating a table for x and y coordinates, right? And we generally have our y equals in standard form or slope-intercept form of an equation. So our y coordinate is always the letter that's to the left of the equal sign. So in this case, because we have a to the left, we're going to put a on the left side of our table. And we generally would have x on the right side of the equal sign. In this case, we have t, so we're going to put t on the left of our table. And we'll just choose 4 points. It doesn't matter which 4 points you use. We're going to choose 0, 1, -1, 2. And now we're going to substitute each row. We're going to substitute the values of t in order to find a. So when t is 0, we have a equals 9 minus 0 squared. And 0 squared is just 0. So a equals 9 minus 0, or 9. So in our first row, we will put 9 where a is. Now when we substitute 1, we'll get 9 minus 1 squared, and 1 squared is just 1. So 9 minus 1 would give us 8. 8 we place in that second row. Letter A is equal to 8 when t is 1. Next, we're going to substitute -1 for t. We'll have a equals 9 minus -1 squared. And -1 squared, -1 times -1 is just +1. So we get 9 minus 1, or 8, again for a. So a equals 8. And now when t is 2, we'll have a equals 9 minus 2 squared. 2 squared is 4. So a equals 9 minus 4, or 5. All right, so here we have 4 ordered pairs. And now we will perform similar steps for the second relationship. We have z equals 1 over m squared plus 3. Again, this letter that's to the left in our table, we want to place that number on the right side. So we'll put our z on the right and our m on the left. And we're going to just substitute 4 values for m. We'll use the same 4 points: 0, 1, -1, and 2. Now when we plug in 0 for m, we get z equals 1 divided by 0, that's 0 squared, plus 3, which equals 0 squared is just 0 plus 3. So that becomes 1/3. So when m is 0, z is equal to 1/3. Next, we're going to plug in 1 for m. We plug in 1 for m. When we plug in 1 for m, we'll get 1 divided by 1 for m, so 1 to the second power plus 3. And that equals 1 to the second power is just 1, plus 3 in the denominator. That gives us 1 1 plus 3 in the denominator gives us 4. So when m is 1, z is 1, 4. Next, we're going to plug in -1 for m. And we'll have z equals 1 divided by -1 to the second power plus 3 in the denominator. So -1 to the second power. And -1 to the second power. -1 to the second power is just 1 plus the 4 plus the 3. So in our denominator, we have 1 plus 3. That'll give us 4. And in the numerator, we have 1. So 1, 4 is the value of z when the m is equal to -1, 1, 4. And then lastly, we're going to substitute 2 for m. So we'll get 1 divided by 2 to the second power. So that's 2 squared plus 3 in the denominator. Now 2 squared is 4 in the denominator. 4 plus 3 gives us 7. In our numerator, we have 1. We just carry over the 1. So we'll get 1, 7. And we're done. 1, 7. How many ordered pairs could you have listed for each of these scenarios? You could have listed an infinite number of t's, an infinite number of m's, and then solve. All right, just like the last example, you can plug in any number from 0 on up, negative numbers and positive numbers. So you can plug in any digit from negative infinity to positive infinity. So there are infinitely many options you have here. Infinitely many. All right, we want to plot these points, and we want to know if this picture represents a finite relationship, meaning that we can count the values we see, or if there's infinitely many points and we can't figure out how many they are. So our first ordered pair is 0, 1. Remember, all of these ordered pairs will have an x and a y coordinate. So 0, 1, 0 on the x-axis, 1 on the y-axis will be right here. We're done with this point. Now 1, 2, 1 on the x-axis, 2 on the y-axis, 1 on the x-axis. Remember, this is x and this is y. 1 on the x-axis, 2 on the y-axis will be here. We're done with this point. 2, 3. So 2 on the x-axis, 1, 2, 3 on the y-axis. 3, 4. So 1, 2, 3 on the x-axis, 1, 2, 3, 4 on the y-axis. -1, 2. I'm going to go over to -1, and then up 1, 2 will be here. Now, is this representative of a finite relationship? Yes, we can count the 1, 2, 3, 4, 5 points that are here. There aren't an infinite number of points, so yes, this is finite. So we can count these points, making this a finite relationship. There's a stopping point that we can see. Now, the domain of a relation is an integer x such that. Now, what would the domain be for the given example here? Domain, remember, is all of these first entries, so all the x coordinates. Our domain we see on the x-axis What's our lowest number we place on the left, and our highest number we place on the right. The smallest number we have for our x coordinate, what will that be? -1. So -1. What's the largest number for our x coordinates? What's the highest number on the x-axis? The farthest we move is 1, 2, 3, right here. So our relationships domain would be between -1 and +3. Now the range of this relationship, the range would be all of the second entries. Those are the y coordinates. So looking at the y-axis this time, what's our smallest number? The lowest number on the y-axis is here, right here at 1. So we write 1 on the left side. And then our highest number on the y-axis, what's the highest number we move? When we look at our y coordinates, what's the largest number? It will be 4, up at 4. And that concludes the notes for 1.5.